Okay, good morning, everyone.
Morning.
I'm going to be talking to you guys today about the TCP/IP Internet Protocol Suite. And I'm going to touch just lightly on IP addressing. So, the Internet Protocol Suite is the network model and a group of communications protocols used for Internet and similar networks, like local networks. It's commonly known as TCP/IP because its most important protocols are the Transmission Control Protocol, which is TCP, and the Internet Protocol, IP. These are the first networking protocols defined in the standard. It's occasionally known as the DoD model because the development of the networking model was funded by DARPA, which is an agency of the United States Department of Defense. TCP/IP provides end-to-end connectivity specifying how data should be formatted, addressed, transmitted, routed, and received at its destination. The functionality has been organized into 4 abstraction layers, which are used to sort all related protocol according to the scope of the networking. From lowest to highest, the layers of the model are the link layer, which contains the communication technologies for a single network segment or link, the internet layer, which connects independent networks, establishing internetworking, the transport layer, which handles host-to-host communication, and the application layer, which provides process-to-process application data exchange. The Internet Protocol Suite resulted from research and development conducted by the Defense Advanced Research Projects Agency, or DARPA, in the late 1960s. After initiating the pioneering ARPANET in 1969, DARPA started work on a number of other data transmission technologies. In 1972, a guy named Robert E. Kahn joined the DARPA Information Processing Technology Office, where he worked on both satellite packet networks and ground-based radio packet networks. And he recognized the value of being able to communicate across both. In the spring of 1973, a guy named Vinton Cerf, the developer of the existing ARPANET network control program protocol, joined Kahn to work on an open architecture interconnection model with the goal of designing the next protocol generation for the ARPANET. By the summer of 1973, Kahn and Cerf had worked out a fundamental reformulation in which the differences between network protocols were hidden by using a common inter-network protocol, and instead of the network being responsible for the reliability of the data transmissions, ARPANET made the hosts themselves responsible. So, in 1975, a 2-network TCP/IP communications test was performed between Stanford and University College London. In November 1977, a 3-network TCP/IP test was conducted between sites in the US, the UK, and Norway. Several other TCP/IP prototypes were developed at multiple research centers between 1978 and 1983. The migration of ARPANET to TCP/IP was officially completed on, on New Year's Day 1983, when the new protocols were permanently activated. In March of 1982, the U.S. Department of Defense declared TCP/IP the standard for all military computer networking. In 1985, the Internet Advisory Board, later renamed the Internet Architecture Board, held a 3-day workshop on TCP/IP for the computer industry, attended by 250 vendor representatives, promoting the protocol and leading to its increasing commercial use. IBM, AT&T, and DEC were the first major corporations to adopt TCP/IP, despite having competing internet protocols. In IBM, from 1984, Barry Appelman's group, I believe was the guy's name, did TCP/IP development. He later moved on to become the head of AOL after they did this. They navigated the corporate politics to get a stream of TCP/IP products for various IBM systems, including OS/2. At the same time, several smaller companies began offering TCP/IP stacks for DOS and MS Windows. The first IBM TCP IP stack came from the University of Wisconsin. The spread of TCP IP was fueled further in June 1989 when AT&T agreed to place the TCP IP code developed for Unix into the public domain. The vendors, including IBM, included this code in their own TCP IP stacks. Many companies sold TCP IP stacks for Windows until Microsoft released a native TCP IP stack in Windows 95. This event was a little late in the evolution of the internet, but it cemented TCP IP's dominance over the other protocols, which eventually just disappeared entirely. The functionality of TCP/IP is organized into 4 abstract layers. We call this the TCP/IP model. The first layer is the link layer, which describes the protocols used to describe the local network topology and the interfaces needed to effect transmissions of internet layer datagrams to next neighbor hosts, which basically means it defines how communications will occur across the local network. Internet layer has the task of exchanging datagrams across network boundaries. So that's for talking to hosts on the internet or other networks. The transport layer, which is responsible for delivering data to the appropriate application processes on the host computers, which means it's responsible for taking incoming data and distributing it to the correct applications that are using that data. And then the application layer, this is the scope within the applications, within which applications create user data and communicate this data to other applications on another or the same host. So the network interface with the link layer is the lowest component of the internet protocols, as TCP/IP is designed to be hardware independent. As a result, TCP/IP may be implemented on top of virtually any hardware networking technology. The link layer is used to move packets between the internet layer interfaces of 2 different hosts on the same link. The processes of transmitting and receiving packets on a given link can be controlled from both the software device driver for the network card, as well as on firmware or specialized chipsets. These perform data link functions such as adding a packet header to prepare it for transmission, and then actually transmitting the frame over a physical medium. The TCP/IP model includes specifications of translating the network addressing methods used in the internet protocol to data link addressing, such as media access control. The internet layer, the second layer, has the responsibility of sending packets across potentially multiple networks. Internetworking requires sending data from the source network to the destination network in a process called routing. In the Internet Protocol Suite, the Internet Protocol performs 2 basic functions. Host addressing and identification, which is accomplished with a hierarchical IP addressing system, and packet routing, which is the basic task of sending packets of data, which we call datagrams, from source to destination by forwarding them to the next network driver closer to the final destination. The internet layer does not distinguish between operations of the various transport layer protocols. IP can carry data for a variety of different upper layer protocols. These protocols are each identified by a unique protocol number. For example, ICMP, which is your Internet Control Message Protocol, and your Internet Group Management Protocol, IGMP, are protocols 1 and 2, respectively. Some of the protocols carried by APs, such as ICMP, which is used to transmit diagnostic information, and IGMP, which is used to manage multicast data, are layered on top of IP but perform internet working functions. This illustrates the differences in the architecture of the TCP/IP stack, of the internet and the OSI model. The TCP/IP model's internet layer corresponds to layer 3, or the network layer of the OSI model. The internet layer provides only an unreliable datagram transmission facility between hosts located on potentially different IP networks by forwarding the transport layer datagrams to an appropriate next hop router for further relaying to its destination. With this functionality, the internet layer makes internet working possible and essentially establishes the internet. The internet protocol is the principal component of the internet layer, and defines two addressing systems to identify network hosts on computers and to locate them on the network. The original address system of the ARPANET and its successor, the Internet, is Internet Protocol version 4, or IPv4, which is a 32-bit IP address, and is therefore capable of identifying approximately 4 billion hosts. I'll tell you right now, they're all gone. This limitation was eliminated by the standardization of IPv6 in 1998, which added an insane number of hosts. It's almost uncountable. Okay, the transport layer. The transport layer establishes a basic data channel that an application uses in its task-specific data exchange. The layer establishes process-to-process connectivity, meaning it provides end-to-end services that are independent of the structure of the user data and the logistics of exchanging information for any particular specific purpose. Its responsibility includes end-to-end message transfer, independent of the underlying network, along with error control, segmentation, flow control, congestion control, and application addressing, which is port version. End-to-end message transmission or connecting applications at the transport layer can be categorized as either connection-oriented, such as in TCP, or connectionless, as in UDP. For the purpose of providing process-specific transmission channels, the layer establishes the concept of a port. This is a numbered logical construct, allowing specifically for each of the communication channels It's a numbered logical construct allocated specifically for each communication channels and application needs. For many types of services, these port numbers have been standardized so that the client computers may address specific services with a server without the involvement of the service announcements or directory services. Because IP provides only a best effort delivery, the transport layer is the first layer of the TCP IP stack to offer reliability. TCP is a connection-oriented protocol that addresses numerous reliability issues in providing a reliable pipe stream. TCP ensures that data arrives in order, that it has minimal error, that any duplicate data received is discarded, that lost or discarded packets are resent, and it includes traffic congestion controls. The user datagram protocol is a connectionless datagram protocol. Like IP, it's a best effort unreliable protocol. Reliability is addressed through error detection using a weak checksum algorithm. UDP is typically used for applications such as streaming media like music or videos or voice over IP or whatever, where on-time arrival is more important than reliability. For simple query response applications like DNS lookups. The applications at any given network address are distinguished by their TCP or UDP port. By convention, certain well-known ports are associated with specific applications. The TCP IP model's transport layer corresponds to the transport layer of the OSI model, which most of you are probably familiar with. The application layer includes the protocols used by most applications for providing user services or exchanging application data over the network connections established by the lower protocols. Examples of application layer protocols would include things like HTTP, FTP, SMTP, and DHCP. Data coded according to the application layer protocols is encapsulated into transport layer protocol units, such as TCP or UDP messages, which use the lower layer protocols to affect the actual transfer of the data. Application layer protocols generally treat the transport layer and lower protocols as black boxes, which provide a stable network connection across which to communicate. Although the applications are usually aware of key qualities of transport layer connections, such as the endpoint IP addresses and port numbers. Application layer protocols are often associated with client-server applications. And the common services have well-known port numbers, which are reserved by the Internet Assigned Numbers Authority, or IANA. For example, HTTP uses port 80, Telnet is port 23. Excuse me. Clients connecting to a service, on the other hand, tend to use ephemeral ports, which are port numbers assigned at random or from a specific range configured by the application. Transport and lower level layers are largely unconcerned with the specifics of application layer protocols. Routers and switches do not typically examine the encapsulated traffic, rather they just provide a conduit. However, some firewall and bandwidth throttling applications must interpret application data. The application layer in the TCP/IP model encompasses the 5th, 6th, and 7th layers of the OSI model, which are the session layer, the presentation layer, and the application layer, respectively. Which you can see here. This is how the TCP/IP model corresponds to the OSI model. Okay, moving on to IP addresses. An Internet Protocol address, or an IP address, is a numerical label assigned to each device participating in a computer network that uses the Internet Protocol for communication. An IP address serves two principal functions: host or network interface identification and location addressing. The designers of the Internet Protocol defined an IP address as a 32-bit number consisting of 4 octets, and this system, known as IP version 4, is still in use today. However, due to the enormous growth of the Internet and the deletion of available IPv4 addresses, a new version of IP version 6, which uses 128 bits for the addresses, was developed in 1995. IPv6 was standardized in 1998, and its deployment has been ongoing since the mid-2000s. IP addresses are binary numbers, but they're usually stored in text files and displayed in human-readable notations, such as 209.168.20.9 or whatever. Decimal notation. IP is a connectionless protocol. This means the devices on the network are not concerned with whether or not the data they send reaches its destination intact. Because of this, IP by itself is an unreliable protocol, as any data packets that are lost in transmission are not retransmitted. Furthermore, the packets are not defined as part of a sequence, so if they're received in the wrong order, they won't be interpreted correctly. TCP provides reliable, ordered and error-checked delivery of a stream of octets between programs running on computers connected to a local area network, intranet, or public internet. And it resides at the transport layer. Web browsers use TCP when they connect to servers on the internet, and it's used to deliver email and transfer files from one location to another. HTTP, HTTPS, SMTP, POP3, IMAP, SSH, and FTP, I believe, and Telnet, and several other protocols are typically encapsulated in TCP, or in TCP. Applications that do not require the reliability of TCP connection may instead use the Connectionless User Datagram Protocol, or UDP, which emphasizes low overhead operation and reduced latency rather than error checking and delivery formation. To establish a connection, TCP uses a 3-way handshake. Before a client attempts to connect with the server must first bind to and listen at a port to open it for communications, which is called an active open. When setting up a connection, something called a 3-way handshake occurs. The active open is performed by the client sending what we call a SYN, or a synchronization request, to the server. The client sets the segment sequence number and this data packet to a random value, which we'll call X. In response, the server replies with a SYN-ACK, which is a synchronization acknowledgement. The acknowledgement number is set to 1 more than the received number, So if the first number was x, the next one would be x plus 1. And the sequence number that the server chooses for the packet is another random number, which we'll call y. And then finally, the client sends an ACK or an acknowledgement back to the server. And the sequence number is set to the received acknowledgement value, i.e. x plus 1, and the acknowledgement number is set to 1 more than the received sequence number, y plus 1. At this point, both the client and the server have received an acknowledgement of the connection, and then communications are established. Really briefly about ports. A port is an application-specific software construct. These are not physical ports on the back of a machine. These are software ports that serve as a communications endpoint in a computer's host operating system. A port is associated with an IP address of the host, as well as the type of protocol used for communication. The purpose of a port is to uniquely identify the different applications or processes that are running on a single computer, which enables them to share the single physical connection to the packet switch network that they're using on the internet. So in summary, TCP IP is the language that provides end-to-end connectivity for network devices. It was created by DARPA in the late 1960s. It's organized to layers in the TCP IP model. It uses 32-bit in the case of IPv4 and 128-bit numbers for the addressing scheme. Addresses can be statically or dynamically configured, which means you can set a permanent static address that does not change on a system, or you can request that an address be assigned to you by a DHCP server every time the host starts up. TCP ensures data integrity. It ensures that data packets that are lost are retransmitted. And then applications use port addresses to communicate across the network from one host. Any questions? Okay, that's all I have for you guys.